Hi everyone, my name is Jiao Lucis Li, and I'm from University of Sciences and Technology of China. Today, I'd like to introduce one of our work in AI for System project, accelerating rule matching system with LearnRanker. From our experience, AI-based optimizer could be a system building block integrates into a system that helps it work better. In this paper, we designed a LearnRanker to re-rank the job processing order to speed up the system. In the real world, rule matching systems have already been widely used in different areas. For example, in Internet of Things, the system provides a rule-based engine for IoT device management and sensor monitoring. And system monitoring, it provides ability to configure one or more system event matching rules specifying which events to monitor. And intrusion detection systems, it provides a set of attack detection rules for web application firewalls. In this work, we pay more attention on intrusion detection system, especially OWASP and Snort, which contains hundreds of rules to check the incoming packet to protect the back-end service. The rule set structure in IDS system is composed of unnested rules like the rule 1, 2, 3 on the right and the nested rules, such as rule 4 and 5, 6, and 7 on the right. There are hundreds of handwritten rules in the systems, and they are mostly independent of one another so that they are easy to be modified for the users, which also introduce the possibility to reorder the rule set next. And the type of rules include IP detection, stream marching, and regular expression add. Like the regular expression rule from OWASP here is an example that will be checked in different fields such as cookies and ads. The rules of IP detection and stream marching could be checked very fast, while the regular expression rules are quite expensive and they make a large portion of the rule set. As the number shows in the table, there are 24% to 35% rules are regular expression rules in OWASP, TRS, and Snort. Regular expression rules have a large range of size from bytes to kilobytes, and the rules contains lots of qualifiers and dots that leads horrible backtracking problems. As you can see on the table, there are thousands of dots, stars, and plus characters in the entire rule set for both OWASP and Snort. One typical situation of the backtracking problem is RE-DOS. It's kind of like a DDoS attack. Attacker crafts molecular strings to target a regular expression rule, and it increases process latency from microseconds to seconds until timeout. After introducing the rules, let's talk about the workflow of typical IDS systems then. There are three main components in the system. Packet interpreter for parsing the incoming network packet, splitting the incoming packet into fields, and the attack detection for processing rules, and the logging for recording the result. Of course, the attack detection is the most important and expensive part of these three parts. Specialized hardware supports other parts runs on it, and filter could catch the certain unmatched rules from rule set, while machine engine and part marching will do the rule matching things for the rest of the rules. The end-to-end latency of the attack detection is followed by the formula. The matching process terminates once a rule is matched or all rule has been checked. Okay. The state of the art rule matching optimization are mainly focused on the part in attack detection we've just discussed. First, just-in-time compiling can greatly speed up part marching, and the filter could pre-filter certain unmatched rules by quick stream marchings to reduce unnecessary part marchings. And to optimize multi-regular expressions marching, hyperscan multi-marching process groups patterns and executes them together to reduce overall latency. And for specialized hardware, research adopts hardware-based matching engine like FPGA-based rule engine to achieve high-efficiency resource utilization. So in addition to optimize per rule processing latency, can we customize system behavior with the respect of input? Sure, we could. The matching process normally tracks rules one by one until one rule is matched. Well, with the help of filter in the middle, it removes certain unmatched rules by quick stream marchings. As you can see in the picture, it removes rule 2 and rule 1. That it could reduce the amount of rules that need to be processed in the rule engine. Furthermore, with the help of ranker on the right, we could prioritize matching rule as a top candidate to achieve early termination, and it won't change the result. To evaluate ranker performance, we regard top n accuracy as having a match rule appears in top n order. And the ranker we design could be regarded as a system building block in attack detection, that it won't change too much of the original system. After filter the rule set depending on the input, the ranker could reorder the rest of rules. Therefore, with the ranker inset, we will introduce a new inference overhead where we also reduce the amount of submission that the rule engine could process less rules. To minimize the end-to-end latency, the performance and overhead of ranker should be trade-off. To design a ranker, the first institution is temporal locality heuristic methods like LRU or LFU. LRU and LFU-based ranker reorders rule set based on historical matching rules, and they are good at long-tailed data streams, but bad at uniform distributions. Like the two graphs here, with different distributions, the rankers' performance are very different. Both of them could achieve more than 90% top 5 accuracies in long-tail distribution, while in uniform distribution, their performance of top 5 accuracies are less than 20. So in the real world, attackers' traffic patterns are hard to predict, so rankers shouldn't estimate input futures instead of assuming data stream distributions. To extract the features of input for reordering the rules, the ranker problem should be regarded as a classification with possibilities. We next think about the traditional machine learning algorithms. Logistic regression is a linear binary classification algorithm, while SVM is also a binary classification model where its performance depends on the kernel we use. Both of them are easy to be trained, and their inference latency for a single model is quite fast. And they are good at classifying either patterns like string matching, regular expression without too many qualifiers and dots. So the disadvantages of them are clearly that they are unsuitable for nonlinear patterns due to the complicated RE rules, and for a rule set with n rules, both logistic regression and SVM needs to have at least n-1 models. That leads the inference growth exponentially. So let's go further. Think about if deep learning algorithm could work better. Fully connected neural network and recurrent neural network are suitable as a rank model. They both multi-class classification models with the softmax function. And their advantages are they are good at classifying complex patterns, easy to adapt variance rule set and data sets. And the recurrent neural network supports unlimited input size. But there are also shortcomings, like high training costs. A well-trained model needs well-trained training coverage and suitable training iterations. And they also have high inference cost, because a deep learning model takes a lot of computations that leads high latency. So from the previous discussion, the learning algorithm that could help building a suitable rank model, in order to get the optimal model, we'd like to introduce the training process. We built a generation to create input and a trainer to select and train model greatly. There are two parts in the input generation. Generator can create an input from trace back the NFA and DFA paths to ensure match the regular expression pattern, because artificial data sets may not provide sufficient insights to learning decision boundaries, and the logged real-world system workloads may not cover all cases. And the transformer could enhance the input by shifting, replacing, appending, and removing characters from the generated input. We need that because current generator generates input from a regular expression hardly achieves well-path coverage. Once a model has been trained, it will be evaluated by a ranker, and the ranker will feedback the performance. The training process will decide when to stop training and return a ranked model. In the end, I'd like to present the evaluation results. Here is a table for evaluation setup that we use hundreds of rules from OWASP and SNORT, 2 rule engines, PCRE with and without JIT optimizer, and E2 from Google. First of all, we like to present the trade-off between rank model and end-to-end performance. The example here we evaluate with different fully connected neural networks. As we discussed before, our final optimal target is to minimize end-to-end latency of the rule engine And the different rule sets result in different optimal ranker model structures, such as the graphs below here that show the optimal fully connected model of CRS is bigger than SNORT. The model of CRS is with nearly 400 neurons per layer, where for SNORT, the model needs less than 100 neurons. And for the next evaluations, numbers are presented are all from the best models. The accuracy compression of learned models here for two rule sets present that because of the multi-classification we discussed before, logistic regression needs many models to handle the rule set. And as a result, the inference latency of logistic regression in total is even higher than the neural networks. And since the recurrent neural network has the highest accuracy, the model inference latency almost 3 times slower than fully connected neural network, while they have only 2% difference of top 5 accuracy. And the performance gains from learn ranker here, we'd like to present the average reduction in the number of regular expression rules that the machine engine needs to process for each input for different rule sets, that with the help of high accuracies, the number of processed rules could be reduced more than 90%, and the average reduction in latency for matching one input on different rule engines for CRS, that with the learn ranker, we could achieve loss reduction of end-to-end latency. And for more evaluation, you can take our paper. You can take a look at our paper. During this presentation, we believe that the system behavior should be tuned to suit inputs, and we explore the potential and flexibility of learn ranker as a building block for rule matching systems. And we presented the trade-off between models and rankers' performance and the system performance gains from the learn ranker. And thanks for watching. I'm not sure if that's too fast.
All right. Do you have some questions?
Hi. Nice job, and I really like this idea.
Thank you.
I have a question. What would happen if I train the network on generator built from data set 1 of rules, and then apply it to a different set of rules, right? You had 2 sets of rules, right? And I can't remember the names, I'm sorry. You had 2 different sets of data, right?
Yeah.
What happened if I train it on one, then test on the other?
Yeah, you're right.
What would happen? Like in terms of like, will it work?
Do you mean we have 2 rule sets and then train for one rule set, but
Yes.
the other testing on the other rule set?
Yeah, because you mentioned that we cannot predict the attacker.
For the deep learning algorithm, I think it will lead some horrible results because the model never knows what the other rules.
So okay.
So from our result, the results are coming from the same rule set because we regard the ordering problem as the classification problem. So every output they should know which rule they are expressed. I think, yeah.
All right, thank you.
All right, I have a question. Oh, has this been used in production, or have you only tested with it?
Now it's a test on the test environment, and we plan to deploy on induction maybe months after. Yeah.
How hard will it be? Like for like the normal operators that are operating these servers, how hard is it going to be to actually put it into practice?
In fact, I think it's a bit hard because in the production there has a lot of limitations. But if you just reorder the rule set, it's quite easy because there are only, I remember there are only 2 or 3 lines for the rule matching loop, and we just put our algorithm in before the loop. That will be okay.
Okay. All right. Well, thank you.